Hello, my name is Blaine Miller, and I'm here to talk to you about coordinate frames and transforms. This is all about spatial information, how is it represented in code, and what is the language in which we talk about where things are. This is not only useful for the software team, but this is going to allow you to talk to the mechanical team as well. So, as it says there, where in the world is my robot? So, when we work with spatial information, it all comes down to position orientation. There are two components to anything's position in space. First off, it's position, obviously, and second, it's orientation, how it's positioned and which direction it's facing. So in order to have all of these values in code, we need to express them in a way that can be used by code, have standard math applied to it, and really we just need a way to turn all of these spatial information into numbers. So I'm going to tell you about how we're going to represent the position and orientation in numbers and some basic mathematical operations that we can use on them. So what we need for all of this is a 3D coordinate frame. This has a defined origin, an x, y, and a z axis, and through this we'll be able to represent a position with three numbers. So as you can see on the left, I have defined a coordinate frame for this screen in 2D, not in 3D. It has an origin at this point right here. This point is defined as 0, 0. To the right is defined x, and up is defined as y. So now we can define any point on this screen with coordinates specified by this coordinate frame. So with spatial information, I'm sure you've heard this before, but it is all relative, and that is why we need to use a coordinate frame. I can say that this point is 2, 3, but that makes absolutely no sense unless we define the frame that it is relative to, which is this point here, x to the right and y up. And of course we need units, but we always use meters. So we've talked about how to define position relative to a coordinate frame. How do you define orientation? So with orientation, there's a few ways to represent it. Euler angles, which are roll, pitch, and yaw, quaternions, and rotation matrices. And there's more, but these are the main three that we're going to be working with. And really, this represents rotations. Of course, just like position, this is all relative, so we will need to define some 3D coordinate frame that this is all relative to, but then we will either represent our rotation as roll, pitch, and yaw, which roll is, rotating about the x-axis, pitch is rotating about the y-axis, and yaw is rotating about the z-axis. We also have quaternions and rotation matrices. Rotation matrices are useful because you can take a point in space as a vector, take the dot product with this rotation matrix, and it'll return a rotated matrix. I'll talk about this more later, but these are the different ways that we can represent orientation. So now that we know how to represent position and orientation, how do we represent the pose of a body? Like, how do we represent where our robot is in the water? And by pose, this is a very special term. It means both position and orientation, the information together. Pose won't just tell you its position, it will also tell you which direction that something is facing. So when in the code we want to represent the pose of a body, we actually define a secondary coordinate frame. So as you can see here, we have our coordinate frame for the world, and then here we also have the coordinate frame for puddles. This coordinate frame here is x going this way, y going this way, and z up, but puddles has x facing forward, y to the left, and z going upwards. This is really useful because by having this coordinate frame change over time, not only will we be able to know where the robot is and which way it's oriented, we'll also be able to express the position of things relative to the robot because it is a coordinate frame. So for example, in this coordinate frame, we can have the point 100, which is 1 meter in the x direction, and that represents something right in front of the robot. And as we'll talk about later, we'll be able to convert that point into the world frame to know where that point is in the world rather than just with respect to puddles. So when I say that we represent the pose of all bodies with coordinate frames, I mean everything in the robot is a coordinate frame. So I'm just going to show you here the thrusters. Here are how we represent our thrusters. Of course, our thrusters have a position on the robot, and they also have an orientation. That is, which way do they exert forces, which way do they blow water. And so in code, we once again make a secondary coordinate frame, puddles thruster 2, that will show where is the position of that thruster and which direction will blow water in. And this is very useful as well because we can take a vector 1, 0, 0, or 1 in the x direction, 0 in the y and z directions, and rotate that into the puddle's coordinate frame to know which direction is it actually going to exert a force on puddles. So to represent all of these coordinate frames in code, we have a tool called TF. TF is it's the tool in ROS that will actually take all of these coordinate frames, recognize the transforms between them, and update it with time, and even keep track of where the transforms between things were at different points in time. So since every coordinate frame has a transform or a defined mathematical operation to define what the second transform is in the first transform. So for example, when we define where puddles is in the world, there is a transform between these two. And so when we define all these coordinate frames, we would define them with respect to another coordinate frame because everything's relative. We have the world up at the top, which is just a defined coordinate frame. It's not relative to anything. It's what we define as our absolute coordinate frame. So when we define, for example, where is the thruster with respect to the origin on puddles, we can translate that back to the world by navigating up this transform tree. So, for example, here, we know where the thruster is with respect to the origin, we know where the origin is with respect to the base link, and then we know where the base link is with respect to the world. Ignore this ODOM, it's a weird little trick that we do. The world and ODOM are exactly the same thing at this moment. So, we can navigate up this tree to figure out where is the thruster in the world, or even where is the IMU with respect to the world. So I've talked about coordinate frames, and I've talked about the transforms in between them. But we need to define some standards first. So there's an x, a y, and a z, and the x, y, and z will always follow the right-hand rule, which I'm sure you've heard of before. So how does this map to our world frame, for example? Well, the red is our x direction, the green is our y direction, and the blue is our z direction. And this will actually follow your right hand. If you make this little hand signal, point your x in the direction of the red vector, your thumb in the direction of the z vector, you'll see that your middle finger will point in the direction of the y vector. And this will follow the same pattern with puddles. X, y, and z will always be in these directions, and that is what is defined as our coordinate frame. In terms of why the world is facing this direction and why puddles is facing this direction, that is what is defined as the standard. When the world frame, we follow the east-north up standard, which means our x direction is facing east, our y direction is facing north, and our z direction is facing up. There's another option of northeast down. However, Ross likes to use east-north up, so we use east-north up. So anytime you have to wonder where is the x direction pointing in the world, that will always be facing east. Whereas the y direction, that will always be facing north. In terms of the coordinate frame of the robot, that is obviously not always facing east, because if it was, the robot would always be facing east. We want a coordinate frame that is attached to the robot, so the coordinate frame that we have defined is that x is facing forward, z is facing up with respect to the robot, and so the y direction is going to be pointing in the port direction. This is how we define our coordinate system on the robot, and any coordinate that you want to specify, such as the coordinate of this thruster, will have a positive x because it's in this direction, and a positive y because it's in that direction. We do have an origin on the robot. It's different for each robot. This base inertia is actually representing the center of mass. Our origin is actually, for puddles, this back left foot. And then finally, how do we represent rotations? Which is the positive rotation, what is the negative rotation, and which axis is our rotation about? So there's also a right-hand rule for that. If we stick our thumb in the z direction for puddles, and this may be backwards in the video, I'm not exactly sure, our fingers will curl in the direction that puddles will curl when it is moving positively about that axis. So when we have a positive rotation around the x-axis, that would mean that puddles is rolling towards us, or these thrusters will be moving towards us, and these would be going down. That's the same as puddles rolling onto its right side when it is a positive x rotation. Same thing with y. If we point our thumb in the direction of the y-axis, curl our fingers, they are going in the direction that puddles is going to start facing down, or going downwards. And finally, when we rotate around the z-axis, we check our fingers, and puddles will be turning to the left. So finally, let's get to the important part. How are you actually going to be using this information on the team? Well, you're going to need to be telling the control system where to put the robot And so that means you need to tell it its position and you need to tell it its orientation. To say the position, that's pretty easy. You just need to say where is Puddle's position with respect to the world. For example, in this case, this would have a negative x, a negative y, and a negative z. And I'm not exactly sure what the numbers are because there are no units on this, but you will be able to tell the robot, for example, if you just want it to go straight down, you would take its current position and subtract 1 meter in the z direction. I want to go 1 meter down. In terms of how to express its orientation, that's a little bit more difficult. So I'm going to go to a visualization tool to help us see that. Orientations are with respect to the world frame, just like with positions were with respect to the world frame. What orientations really are is you are translating this set of x, y, and z coordinates to a new set of x, y, and z coordinates. For example, here, if I want my x to be now over here in this direction, I will need to rotate by 90 degrees around to the y-axis. So the way that we represent Euler angles, or the way that we represent orientations, is with Euler angles or quaternions or rotation matrices, but I'm going to show you Euler angles first. Euler angles can be broken down into rotations around each of the different axes. The roll, pitch, and yaw are rotations around the x-axis. Pitch, in this case, is the rotation around the z-axis, but in our coordinate system, that's a y-axis. And then yaw is about the vertical axis, which is, in our case, z, in this case, y. So that is why rotating around the y-axis pointed us in this direction. That was 90 degrees of yaw. If we want to break this down, any orientation down, you will have a roll, a pitch, and a yaw number. So for example, we are going to do 25, 73, and negative 50. And this is going to be some arbitrary rotation. You're in this direction, facing down, and roll to the side a little bit. These operations be applied in the order of yaw, then pitch, then roll, which means that first this y is applied, then the z is applied, and then the x is applied. And you can see that because as I change the x number, it is only changing the roll. Meanwhile, if I change something like the yaw, the whole thing, or if I change the pitch, the whole thing is changing. And if I change the yaw, the whole thing is changing even more because this is the first operation. So once again, we can see the 42, 83, negative 37 by applying the order 83 first, then negative 27, and then the 43. And those are the three components that would get us here. Quaternions are definitely more difficult. The reason why they're useful for us is that the math on them is incredibly simple. With Euler angles, we kind of reach some black hole areas where angles kind of converge on each other. For example, here, if I go 90 degrees pitch, changing my y will change your roll, and then also changing your x will change your roll. And of course, that's not exactly what in our coordinate systems where x and y do the same thing. So we have this quaternion. The way to think about quaternions is that quaternions, this number here is sort of the unused part, and then the x, y, and our z are all of the x, y, and z rotation parts. The magnitude of this vector will always have to be 1, so you will always find that the components add to 1. If I want to rotate completely about the x-axis, that way I'm upside down, I put the 1 here instead of in the w, and now that will rotate us completely upside down. And in the same way, if I want to rotate completely around the y-axis, I put a 1 here instead of a 0. Now we've rotated completely that way. If you want to go halfway, this will be half, and the other remaining half will be over here in our w component, because that's sort of the leftover. And of course, this will be normalized so that the magnitude's 1, but as you can see now, we have moved halfway there. And if I change this number to be even less, like 0.2, we will rotate even less. And once again, it was renormalized. The weird part is when all of these start to work together on top of each other. I can't exactly explain how things work then. It's kind of, quaternions are kind of weird and hard to understand. So whenever we are displaying numbers on our own, And like to a user, we will be using Euler angles because they make the most sense in terms of representing orientations. So coming back to this problem, how do we represent this orientation of the robot? Well, once again, with respect to the world frame, it is a rotation from the world frame. So how do we rotate this coordinate frame to this coordinate frame? Well, we go yaw, then pitch, then roll. So we start with yaw. How do we get this x to line up with this x? It's probably like negative 45 yaw, because it is a negative 45 degree rotation around the z-axis. The pitch looks pretty much 0, so the pitch is 0, and then finally our roll, it has been rolled to the right a little bit, which is a roll around the z-axis, or roll around the x-axis by probably about 10 degrees. And then finally that will give us our orientation here. Yaw of negative 45, pitch of 0, roll of about 20 degrees. So that is how we tell the control system to move the robot to a specific pose. How do we tell it other information? For example, if we want the robot to have a specific speed. Well, speed, we actually represent that in the body frame. Position and orientation, those are all in the world frame. They are with respect to the world, because if they were with respect to the body, that wouldn't quite make sense. Because what is the robot's position? Well, with respect to the robot, it is 0, 0, 0. And what is our orientation with respect to the robot? Well, that is 0, 0, 0, once again. However, when we do velocities, we want the velocities with respect to the robot, and that is because we don't care about the robot's orientation when we express its velocity. So when we say that the robot has a positive x velocity, we mean that it is moving forward. We do not mean that it is moving east, we mean that it is moving forward. In the same way, when we say that the robot has a positive x angular velocity, that means that it is rolling to the right. It is not rolling around the east axis, it is rolling to the right on from the robot's perspective. You need to make sure that you keep track of the distinction between the two. If you are ever working with velocity or accelerations, that is in the body frame, and if you are ever working with positions or orientations, that is in the world frame. You now know almost everything that you need to know for the software team in terms of coordinate systems and transforms. If you do ever need to know specific math information, you will be able to Google it with the terms that I have taught you in this lecture today. A lot of the math is just too complicated. Just kind of find an example usage and it will all work out.